This week we will discuss additional statistical techniques that you may encounter with a GIS. We'll start with correlation and regression. In the earlier part of the course, we discussed correlation as one of the outcomes of statistical analysis, along with experimental and so on. There are varying degrees of precision with correlation. We can discuss positive, negative, or none, or curvilinear correlation. And we can also calculate correlation coefficients and develop formula to predict the value of one variable based on its correlate. The calculation of the correlation coefficient is somewhat laborious. You have to determine means, standard deviations, z-scores, and then a cross product of the z-scores, and then sum them up. The z-score is a standardized value that is what we want to compare between the two variables. In other words, the two data sets we have. Compare their standardized scores. This is not the only way, but it's the most intuitive to me. The Pearson coefficient is the sum of the cross products of the z-scores, and we can use that in determining the slope of the line. If you remember from high school algebra, the formula for a line is y equals mx plus b. And so we can use the correlation coefficients to help us determine the m, or the slope of the line. The slope m is calculated from the Pearson coefficient, and it's equal to the Pearson correlation coefficient times the standard deviation of y divided by the standard deviation of x. The y-intercept is then calculated as b, that's the y-intercept, is equal to the average y value minus m that we just calculated times the average x value. And then we get all the elements we need for our equation, y equals mx plus b. And with that we can fit a line that best fits the data that we have in our data set. In other words, it might be a set of attribute values that we're looking at in a particular GIS table or layer, or even between layers. The regression line is the equation for the best fitting line for a data set. The equation is based on determining the slope and y-intercept for the best fitting line. And again, it's y equals mx plus b. So, regression analysis is a tool that enables one to predict an individual score on one variable based on knowing one or more other variables. And here we see the calculation for determining it. This is in Excel, and obviously there's packages for a GIS that do these calculations for you. Okay, let's go on to time series. The time series is a sequence of data elements from a succession of observations over time. Many data sets have a special structure. They are organized by time and location, where location can refer to a method of roll-up and drill-down, such as geographic regions, sales territories, product lines, advertising campaigns, and so on. A time series analysis is not time series regression, although it may use regression that we just talked about for some of the patterns. Time series analysis is a set of methods that focus on one measure of interest and its patterns over time. Are there trends, seasonality, or cycles that one can measure in a time series? Once we understand an individual time series, then we can look for possible relationships between different time series. A useful pattern between two series is a lag effect. In this case, one series makes a move before the other, and depending on the predictability of this, we can use the first mover as an indicator for the moves in the other. So when people say time series analysis, they're usually talking about methods that try to identify a trend, and that can be a smooth function that captures some persistent change. Can also be talking about seasonality. That's a periodic variation, possibly including daily, weekly, monthly, or yearly cycles. Generally, analysts work with time series by observing trends and cyclical patterns in the data, and from this past data predict the future. Variables of interest might be sales dollars per time period, sales volume, time to sale, or market share. Our first step is to gather the data and look at it visually to see overall patterns and impressions. After viewing the plots, forecasting the future is the next step. Obviously, there is great uncertainty with the future, and the longer our time horizon, the greater the uncertainty. The value of a forecasting model based on time series analysis is determined by the quality of its predictions. Here we see a horizontal pattern for a time series. It's also known as a stationary time series, and it's, for all intents and purposes, a flat line with random variations around that line. Moving averages and exponential smoothing are forecasting approaches for this pattern. Here we see a horizontal pattern with a level change. Something happened in the environment, and what had been one level all of a sudden changes to another level. So in this case, there's a jump from a low-level horizontal pattern, random variations around a flat line, to a higher level. And then you have random variations around that higher level. And here we see a trend pattern. This is gradual inclines or declines over a longer period of time. And of course you're going to have random short-term fluctuations around that line. These kind of trends can be linear or nonlinear. Linear trends change by a constant amount, while nonlinear changes are non-constant. So one example that we see quite often for nonlinear change is when things change by a fixed percentage. And with a trend, we can then make a forecast by fitting the best line and then going into the future. Obviously, we don't have the random variations around that line, but going into the future, we might predict what the particular value for the independent variable or the dependent variable would be based on the independent variable. Here we see a nonlinear trend, And this, of course, is an exponential increase in values over time. And here a cyclical pattern. And the data shows an alternating sequence of points, and it'll be around a derived line. So we see a line roughly like this, and we see a cyclical pattern around it. It's not random. You see this cycle, and it goes up and down around that derived line. So it's a multi-period recurring set of changes. So some of the forecasting methods we might use. For horizontal, it would be exponential smoothing or a moving average. For trends, it would be a linear regression. And for cyclical, we might assign a categorical variable to each part of the cycle, and then use multiple linear regression for our model. The exponential smoothing method is a weighted average approach to forecasting. The moving average is like exponential smoothing in that it also uses an averaging approach. Both the moving average and exponential smoothing are appropriate for horizontal pattern data series. They smooth out the random variations in the horizontal pattern and are also known as smoothing functions. Linear regression is, as we just discussed, a correlation method that can be used in time series analysis, and it's used to forecast a future value based on historical change. The regression line is the best fitting line through the scatter plot of values over time. Sometimes if we have a non-linear set of values, we can actually transform them into a linear. So for example, if we see something that's increasing exponentially, we can use a log function on that and create a linear regression on the logs of that exponential series. So here's some sources of error that we might get in time series analysis. Sampling error, and that's if we run the experiment again, we expect the estimates to vary. It's just the nature, as we had discussed in our statistics lecture, of these type of statistical experiments. We're dealing with probabilities rather than exact outcomes. There's modeling error. We might be using a model that's not necessarily 100% a good fit for our particular data. Let's look at Bayesian analysis, which is conditional probability, the probability of A happening given that B has happened. And it's used a lot in data mining operations. And there's two types of data mining. There's supervised and unsupervised. In supervised mining, the data has been tagged, so we know what the outcomes are. So we look at a set of attributes and we know the outcome, and then from that we can determine a model that will predict the outcome for another set of variables coming in. So with supervised mining, we divide our data sets into two parts: a training data set that we use to actually train our model, and then the other is a testing data set that we can use to test how effective is our model. Unsupervised mining does not require a training set and does not require an already known outcome. Features are the inputs that we provide to our model. Our goal is to predict an outcome based on the values of these features. There's three categories of features. A simple yes or no, true, false that we can encode as a 1 or a 0. It could be numbers, or it could be a discrete set of options that we make a choice from. There's four prominent predictive modeling tools. Bayesian statistics are suited to yes or no features. K-nearest neighbors are suited to numeric features or a choice from a discrete set of choices. And support vector machines are suited to numeric features or again a choice from a discrete set. And decision trees are a mix of numeric and categorical data. Naive Bayes is a classifier. A classifier assigns new objects to classes. So for example, if we had a GIS data set of areas that were considered risks for environmental, for floodplains, we might have a set of factors we would look at. Then we would create a model, and we might say that, okay, a new area that comes in that we add to our GIS, given these other factors, we might classify it as at risk for flooding or not, based on what we've already observed from our input data. So the naive Bayes is going to have a training set of labeled input that we use to train the algorithm. The algorithm then classifies new unlabeled features into the correct class. Okay, so this is a short overview of some of the more advanced statistical techniques you might see in a GIS. And in our lab, we'll go over how we do regression in a GIS. Thank you.